This is lecture 19, and this lecture is going to be about trees. So we're moving back into the realm of supervised learning. After our kind of short jaunt over into unsupervised learning, we're going to go back to supervised learning. And in particular today, we're going to talk about tree-based methods and some of the basic building blocks of these tree-based methods, which are useful for building more advanced methods. So we'll talk about trees today, and then in the coming lectures, we're going to talk about some of the more advanced methods that can be built upon these. So the first thing we want to talk about in particular is regression trees. And this is a tree-based method in a regression context. And nearing the end of the lecture, we'll talk about classification trees, which basically applies the same kind of tree-based methods to a classification problem instead of a regression problem. So the idea, the kind of basic idea behind a regression tree is that we're going to break up our feature space into a series of rectangles by kind of successively splitting up the space, and we're going to fit some really simple model to each rectangle. So this is going to build us a pretty nonlinear method. So let's just write down our basic idea. Our basic idea is one, we're going to break up the feature space of our possible x's into a collection of rectangles. And we're going to do this by successively splitting dimensions, and we'll see exactly what that means. Successively splitting our dimensions. And our second step is then going to be to fit a simple model to each rectangle. And in the simplest case, which is the one we're going to talk about, basically, we're going to predict the average value of the training data in each rectangle. So I think it's really instructive to kind of first look at just an example of what this may look like. So here, let's have our feature space. So maybe we have two variables, an x1 and an x2, and then we're going to have some observations in our training data. So maybe there'll be a point here associated with some y1, a point here associated with some y2, maybe this will be associated with y3, this will be y4, this will be y5, this will be y6, and maybe y7 is over here. This is basically a toy example where we have two x's, and then we have some training data, which are my points here. And to build up my tree, and we'll get to why it's called a tree, but to build up my tree, what I'm going to do is I'm going to split my dimensions. So first, maybe I'll split on dimension x1. And I'll pick some point to split my dimension on, and so maybe I'll split it here. So when I split it here, I've basically created two half planes. I've created the thing to the left of it, and I've also created the half plane to the right of it. And I'll then split again. Maybe this time I'll split using x2, and I'll split maybe here, for example. That's a place I could split. And again, kind of within this left-hand half plane, I've now created two top and bottom half planes, or rectangles, however you want to think about them. And then I'll split again. Maybe I'll split it on x2 again. That's allowed. I'll split here. So that's a thing I could do. And we don't know why we're splitting where we're splitting yet, but we'll get to that. But after I do this, so I kind of successively, or recursively, go and I split my space up. So now I have a series of triangles, of rectangles, right? So I have the series of rectangles. I can name this R1 for rectangle 1, R2 for rectangle 2, R3 for rectangle 3, and R4 for rectangle 4. And what I'm going to do is for each of these rectangles, I'm going to predict some value. So I'm going to fit some model to my data. And in the simplest case for a regression tree, we're basically just going to predict, our model is going to predict the average value of the y's in that rectangle. So but the general idea is like, if I observe some x in this rectangle R1, my f hat has to make some prediction, right? And the prediction I'm going to make is just going to be whatever the average values of my y's are in that rectangle. So my C1, which is going to be the value I predict, will just be the average of y1 and y2. And so if in the future, after I've built up this model, if I observe some x that lands me over here, I'm going to predict the average of the training data in that rectangle. Here, in rectangle 2, my constant value I'll predict over this entire rectangle will be, I guess in this case, it's just y3 because there's only one thing. That's kind of the average. In rectangle 3, my value C3 would also just be, I guess, y4. And in rectangle 4, the value I predict there, C sub 4, would be y5 plus y6 plus y7 divided by 3, so the average of those. So this feels a little bit like a nearest neighbors approach, and in some ways it is related, in so much as, right, the value that we're predicting in different points is related to kind of the nearby points, right? I've kind of partitioned up my space, not into neighborhoods like nearest neighbor does, but into these rectangles, and the value I predict, say in rectangle R4, is just the average of the training data, or the training y's in that rectangle R4. So I could write this out mathematically. I could say that, say, y hat, which is f hat of x. So for some x, I'm going to build up my f hat, so predict some y hat. And what is this going to be? It's just going to be a constant value, some c sub I, where x is in the rectangle Ri. So that's one way you can write this thing out. You can write it out a little bit fancier. You could say instead sum over all of our rectangles. If I have m rectangles, so here m is the number of rectangles, I'm going to sum over all those rectangles, and then I'm going to have an indicator that says, tells me whether or not x is in each of these rectangles, and I'm going to multiply by that value ci. So this is the same kind of thing. So my indicator here is going to be obviously 1 if x is in Ri, and 0 if it's not. And this, the ci, is going to be the average value of my training y's in rectangle I. So the second form of it is a little more mathematical. It actually allows a little more analysis, so they're not going to use it too much. But the reason you might want to write it in this kind of second form rather than saying it predicts that constant average value in the rectangle, write down words, is you can actually think about trying to, it's a little bit more of a mathematical form if you're trying to analyze the behavior of it. So that's basically the algorithm. or a basic version of the algorithm, is it's basically going to successively split my space up into a series of rectangles. And you could fit other models. The simplest thing to do, the thing that probably works just as well as anything else, is we're just going to predict the average value of the training y's in the rectangles that we've developed. So what you'll get at the end of the day is if I looked at this, for example, in a one-dimensional case, so here I just maybe have some x1, and I could look at, say, f hat of x. In a one-dimensional case, splitting it into rectangles would just be splitting my space somehow into segments here. And if my training y's in this one-dimensional case, I don't know, maybe they look like this. This is y1, this is y2, maybe there's a y3, a y4, maybe a y5, and a y6 over here. So these are maybe my training data points. If I had split with these rectangles, as given by these red dividers here, I would get a model that predicts the constant average between, for this rectangle, of y1 and y2, and the average value of y3 and 4 over this rectangle or segment. And then I guess this average is lower, right? This is maybe the average down here. So basically what we have is a step prediction function. And if you did this in more than one dimension, if I had an x2 or an x3 and an x4, you basically get some n-dimensional steps. So it is predicting, in some ways like a nearest neighbor algorithm, it predicts a constant value across the rectangle. So you're really going to get kind of the staircase looking thing in 2 dimensions. And the natural question that arises with the algorithm we've described so far is, why do we call this a tree? And the reason we call it a tree is you can represent it as what's called a binary decision tree. So we can represent binary decision tree. So let's look at an example. So let's, on the left here, have my space again, x1, x2, and I don't know, let's have some kind of rectangles we split up here. This is R1, R2, and then maybe we could split with this, R3, R4, and I predict my constant values in each of these, C1, C2, C3, C4. And I've split, for example, let me redraw this red line here. Let's say that I split along the x2 direction at T1, and I've split along the Rx1 direction at, let's say, this is a T2 and this is a T3. Okay, so these are just the values at which the points on these axes at which I split. So I could write T1 over there, right? Something along those lines. And it turns out you can represent, when you break it up in this triangle like this, you can represent this as a kind of binary decision tree. So here is the root of my tree. And the first split is this split at T1. I check either x2 is less than T1 or x2 is bigger than T1. So my first split is into two nodes. One, x2, we follow this if x2 is less than or equal to let's say if it's greater than or equal to T1, and we follow x2, and we follow this other one if it's less than, or let's just say less than T1, right? So either I split, my first split is, let's say, on this T2 axis, where I split, I either go above it or I go below it. If I go above it, so x2 is bigger than t1, I have two decisions. Either, then I look at x1 and I say either x1 is I'm either in rectangle 1 or rectangle 2, right? Either x1 is bigger than t2, in which case you're in R2, or less than t2, in which case you're in R1. So you look at x1, you say, is it bigger than or equal to t2, or is x1 less than t2? And so in the case where first I say x2 is bigger than t1, so I'm above this middle line, and then if I'm bigger than, x1 is bigger than t2, I'm in rectangle 2, and so I'm going to predict c2. If my x1 is less than t2, I'm in rectangle 1, and so I'm going to predict c1. And we could play this game with the other node, right? If x2 is less than t1, I'm below this middle red line. And then I'm either to the right or the left of t3. If x1 is bigger than or equal to t3, or x1 is less than or equal to t3. So if x1 is bigger than t3, that says we're in rectangle R4. And that ends up predicting c4. Or if I'm sorry, that should be over on this one, right? If x2 is less than t1 and x1 is bigger than t3, we're in R4, and so we're going to predict out c4. And if x1 is less than or equal to t3, then we're in rectangle R3 and predict c3. So it's a little bit tedious, but you can do it. And so you can go back and forth either way, right? If you give me this series of rectangles, I can give you this decision tree. Or if you give me the decision tree, I can give you the series of rectangles. So I think visually it's nicest to, well, both ways are useful. But sometimes it's nice to visualize it as this breaking up the rectangles, and you decide a step height on each rectangle, which is the value you predict. Or you can think of it as the decision tree. But it's a pretty simple algorithm. Nonetheless, it can work actually quite well in practice. So that's the basic approach. We haven't really nailed down some of the details. And our goal, kind of overarching goal, is we want to build a good tree. All right. And so the things we need to do, let's say we need to decide, one, which variable to split on. Because the way we build up this tree, or alternatively our set of rectangles, we pick a variable and we split the bit space at a certain location. So the first question is, which variable do I split on? And we kind of do this recursively. We split, and then we look at the subtriangles, we split, and we split. So which variable do I split on? Where do I split this variable? You can say when. I say when, maybe where. Where do I split this variable? And 3, when do I stop? That is how many splits. How big to build this tree. So obviously, the trivial answer for all these kind of combinatorial things is that the globally optimal approach is to consider all possible trees and choose the best. This is obviously not computationally tractable. So unfortunately, we can't just look at all possible trees and choose the best one. What we're going to actually use is some, and maybe I'll call it somewhat, greedy approach. We'll talk about it. Okay. So we need to determine the first two questions first is basically, how do we even get this procedure up and running? How do I choose which variable I should split on when making my rectangles? And how do I choose where to make that split? So let's define R1 of JT and commensurately R2 of JT to be the half spaces formed by splitting on variable j, variable xj at point t. So what does that look like? Here is an axis, here is my variable xj, and if I split that variable at point t, I would basically be splitting that dimension of the space into two rectangles, R1, JT, and R2, JT. So these R1 and R2 are just going to be my my two rectangles to the right and to the left, as it were, if I split that variable. We can define, furthermore, we can let the RSS of splitting variable j at point t, this is just going to be the RSS of splitting of the one side and the other side. So the RSS of splitting variable j at point t is the RSS that we attain, basically. Right, so there'll be some points here in my training data. There's some points on one side, there are some points on the other side. And obviously we predict on each side by just predicting the average value of these points. Now that won't perfectly predict all of those points in our training data. Some of them will be wrong. And so you can calculate the RSS, basically you calculate the value of, of the true y at each of these points minus what you predict, square it, sum it up. That would be the RSS for each of those two halves. So if we can even write this out, right, what this would be mathematically, let's say, is this is sum over I, where xi is in R1 JT, and it's going to be corresponding yi's minus whatever value we predict. Let's just call it C1, we'll predict on the left. And then the RSS for the right side is we're going to look at I, where xi is in the right side, R2 JT, and we're going to look at the sum of the squares. So C1 and C2 are the values predicted in right and left above, right? So if I were to make, so the idea is with this RSS at splitting variable j at point P, T, is that what we're going to do is we're going to calculate the total RSS, which is just the RSS split of each side, which is that if I were to split variable j at point T, then what would be the RSS that I'm going to predict in each of these two rectangles, the average of the y's in one rectangle and the average of the y's in the other. What would be the RSS if I make that split on each side? So that's basically what this RSS is calculating. So it turns out, right, so I kind of formulated this pretty general in terms of the C's. It turns out, to minimize this, we've seen stuff like this before, to minimize RSS, no matter how we make our split, C1 should be the average of my y's in the left-hand side, and C2 should be the average of my y's in the right-hand side. So when we initially described the model, you go back way up to our beginning, we had just said we're going to split the space into these rectangles and we're going to fit some simple model. Or even more concretely, we're going to predict some constant value in each of the rectangles. Now, I claimed here that what we're actually going to do at the end of the day is we're going to predict the average value of the y's. But there's no why predict the average value of the y's. It's the question. The question is, and the answer is basically that if I want to minimize this RSS, actually setting the constant value I predict in the rectangle to minimize the RSS is going to, we're going to set the constant value to the average of the values in the rectangle. So why you might want to keep more generous, you can kind of make that point, which is that, okay, we're predicting the averages because that would minimize the RSS for each of these two sides. But basically the algorithm we're going to do is, our algorithm here to build the tree is we need to choose, of course, j and t, right? So for a specific split of variable xj at point t, okay, we should choose the c's so that they're the average of the values in the resulting splits. But how do we choose j and t? That is, how do we choose which variable xj to split on, and how do we choose where to split that? So those are the first two questions here. Which variables do we split on, and where do we split them? And basically, we're just going to do a search. So the answer, so what we're going to do is 1 for each variable. We're going to do a search over possible, that's supposed to read, do a search over possible t values. So one way to think of that is, in this diagram here, it'd be like moving t back and forth. We're just going to scan t back and forth over this axis, and we're going to find, and we're going to calculate the RSS for each possible split of this variable, jt. And 2, so not only to search over the possible values of t, we're going to do it over each variable. So for each variable and over the possible t, we're going to calculate this, and then we're going to choose j and t to minimize this RSS. So it's not that much more complicated than that. So what basically the idea is, we're going to start with data. We're going to look for each variable. We're going to do a search over over the axis, and we're going to look for the best place to split this variable at. And so we'll do this for x1, search, and we'll say this is the best place to split x1. Then we'll do for x2, we'll go search over the possible places I could split on x2. This is the best place. Split x2, and do the same thing for x3. So we're searching over all j's and t's, finding the best place to split this, and we're going to then choose the j and t to minimize this RSS and make that split. Let's say, and make that split. And the kind of third step here is recursively do this for split data. So after we've made this split, we've now split our data set into two, and we'll recursively do this for each side. So we'll take the data on one side, and we'll recursively build, we'll recursively do this, apply this procedure to that side, and we'll do the same thing for the other side. And so we're just going to kind of recursively do this. Now, of course, you have to decide at some point, when do we stop? Because you could keep recursively doing this on, maybe you don't want to do this forever, right? What are the concerns here? If we have too many splits, what if I do this 1,000 times? I split 1,000 different times. Basically, we're building a very flexible method. Because I've split my space into many thousands of rectangles if I do this. And so the worry here is overfitting. So kind of each time we split, the more splits we make, the more we're dicing up the space into these smaller and smaller rectangles. It'd be like choosing a small value k for k and n. It'd be a really flexible method. If we have too few splits, if we only do this once, so we split it into two regions, right? That's an inflexible method. You only have two different values that you can predict: the average on the right or the average on the left. So if we have too few splits, we have an inflexible method. And our worry here is obviously underfitting, right? And so we need some strategy for determining how many splits we want to make. So here's the bad strategy. Now, before I said we're going to do a kind of greedy approach. Our bad strategy is a very greedy approach. And this would be to set some threshold. That's not how you spell set. Let's say set some threshold and split until our RSS decreases by less than this threshold. So every time I make a split, I'm basically straight up increasing the flexibility of my method. And this is kind of a nested method. So my RSS, my training RSS, is guaranteed to go down, right? I've seen this happen before, where I'm directly increasing, in kind of this nested model, I'm directly increasing the flexibility, and so my training RSS has to go down. It'd be like decreasing k and k and n. That has to decrease my. I guess that doesn't have to do that for k and n, does it? Are they nested models? Maybe they're not nested. But we've seen this in regression. If I increase the number of covariates in my regression, my training RSS has to go down. And same thing, if I increase the number of splits I make, my training, I have an increasingly flexible method in a nested way, and so my training RSS has to go down. So every time you make a split, you're decreasing your training RSS. And you could say, keep going until it hits some threshold. It's not worth decreasing, it's not worth making a split if it's only going to decrease my RSS a little bit. So maybe I should only make splits if they're going to decrease my RSS a lot. So this is basically a very kind of greedy approach where I just keep doing until I hit some hard threshold, then I'm done. Now it's easy. The problem here is that a bad split that only kind of decreases my RSS, this might lead to a better split down the road. And this is not particularly unique to trees. It's just a problem of a greedy approach, which is that a bad decision early on might lead to a better globally optimum solution later on. And so this kind of straight up greedy approach is not typically what's used. The better strategy is what we're going to do is, one, we're going to grow a really large tree. We're basically going to overfit the data. And two, we're then going to reduce the size. Let's say reduce its size, i.e. number of splits. And this is called pruning. So we're basically going to, quote, prune the tree. So typically this is done with what's called cost complexity pruning. So as a little bit of an aside here, just some graph theory, is that a tree T1 is called a subtree of some other tree, T2, if I can get T1 by basically what I would call collapsing part of T2. So here on the left here is maybe my T2 tree, so maybe it looks something like this. Okay, there's my T2 tree. And I could pick part of this. Maybe I'm going to pick this, and I'm going to replace this with a leaf, with a node. So the idea is I'm basically collapsing this down. So what I would get, if I collapse this part of the tree, is I would get another tree that looks maybe something like this, right? Where I've replaced that whole subtree there, the whole part, with a node. So the T1 here is a subtree of T2. So typically we write T1 as a subtree of T2, something like that. So we can do pruning. We could do this strategy with what's called cost complexity pruning. And cost complexity pruning is basically, we're going to minimize, so typically it's denoted C alpha of T, where this alpha here is some tuning parameter. And C alpha of T is basically a penalized version of the RSS. It's basically the RSS for some tree T plus alpha times the size of the tree. So the absolute value bars around this is basically the size of the tree, which is equal to the number of leaf nodes in my tree. Alpha is my tuning parameter, and T is the tree, the putative tree. And what we want to do, the idea with cost. So one way you can you can visualize this is that so it's RSS of this tree. Basically, use the tree to predict your training data, calculate the RSS, plus a penalty term for having too big of a tree, or having a very complex tree. So if T is large, very complex, we have a lot of rectangles, we have a lot of splits, the size of the tree is large, and so that's going to potentially be overfitting, but our RSS would be small. If we have a small tree, absolute value of T, or size of our tree is small, but the RSS will be larger. So you basically it's basically a penalized version of the RSS, and you'd like to kind of minimize this, right? So our note here is that if alpha is 0, what is this going to do? So let me back up and say, basically, our strategy here is going to be given some alpha, some tuning parameter alpha, what we're going to do is we're going to grow a large tree, and then we are going to search over the subtrees and choose the subtree that minimizes this. C alpha T, something like that, right? So this is a way of, you're not searching over all possible trees, we're just going to grow a really large tree, and then we're going to prune it back, and we're going to choose the kind of subtree, to prune the tree. So by pruning here, we're going to look at the subtrees. So this is basically pruning. And we're going to find the subtree that minimizes this penalized RSS. So for the alpha, we'll do that. Our note here is that if alpha is 0, then this whole penalty term goes away. We're just going to choose as large a tree as possible. If alpha is infinity, we're going to choose a tree as small as possible. And obviously in between, we're going to choose some other tree. The other fact here, which I'm not going to go and prove, but if alpha 1 is less than or equal to alpha 2, then the tree that minimizes, that's how you spell minimizes, C alpha 1 of T is, let's call it T1, and if T2, correspondingly T2 minimizes C alpha 2 of T, then T2 is a subtree of T1. So what this means is that the optimal tree is for over values of alpha are nested, right? So what am I saying here? All right, so if alpha is smaller, we penalize less. So we should have a larger tree. So alpha 1 corresponds, if the optimal tree that optimally maximizes this, minimizes the RSS given alpha 1, call that T1. For another alpha that's bigger, we call it the optimal tree over the search, T2. T2 is going to be a smaller tree than T1 because alpha 2 is larger. We penalize it more, we get a smaller tree. Turns out not only is it just a smaller tree, it is actually nested. So the optimal tree with a larger alpha is nested is a subtree of the tree with a larger alpha, or with a smaller alpha. So optimal trees over values of alpha are nested. Is basically the point. So if I have a sequence of alphas, alpha 1 less than alpha 2 less than alpha 3, let's say alpha n, I know that the optimal tree T1 that for that alpha 1, the tree that optimizes my cost complexity, T1 will be large, be larger than T2, is larger than T3, is larger than Tn. So we basically get a nested sequence of optimal trees over values of alpha. So what this means is I can very easily compute, because these optimal trees for different values of alpha are nested, we can easily compute the optimal cost complexity, let's say CC trees over a sequence of alphas. We can easily do that. We can easily compute that. So what this allows us to do is it's really easy to take a whole sequence of alphas and actually compute nested, the kind of sequence of optimal trees. If I chose this alpha, what would my optimal tree be? If I increased it, what would it be? If I increase it, what would it be? And so it's really easy to get a whole bunch of different trees to look at. So we'll see this cost complexity, which is a little bit old school. We'll see in the coming lectures what people do with trees more modern, but these are really a base method for many, and this kind of cost complexity tuning was kind of the old school way of building these trees, and this is a very reasonable way of building trees. Still, if you want to build a tree, and trees are nice because they're interpretable. You have a literal decision tree that tells you the rules of the game and how you make a prediction. So if you ask me, how do I make my prediction? I can show you the decision tree. And if it's relatively small, I can kind of walk, I made this to split, and this is bigger than this, and this is bigger than this. So I kind of walk my way through the tree. So they can be interpretable. So cost complexity tuning is one way. You can also choose your alpha through cross-validation, of course. It's a parameter we can choose. We'll get to next time. Hopefully next time we'll start talking about, if I don't care as much about interpretation, I just care about prediction. These trees have been used as base methods for a bunch of really much more complicated methods that are very popular that you've probably heard of. So before ending the lecture, I just want to talk kind of briefly about classification trees, because this whole discussion so far has been about regression trees, but classification trees are not much more complicated. So here's my example. I have x1 and x2, and maybe I have red circles, and so some of my y's, these are my training y's, are maybe red circles, and then also I have some blue triangles. Maybe this is kind of what my training space looks like. And a classification tree is going to do a similar thing where it's going to recursively split. Maybe I want to split here. Maybe I want to split here. Maybe I want to split here. I don't know. Maybe that's not what I want to do. Maybe I want to split here. Whatever. Right? It's going to recursively make these splits in the same way, but it's going to predict the majority class in each rectangle. So, whereas regression took the average, not surprisingly here, just like K and M took the average, the classification version just predicts the majority class in the rectangles instead of neighborhoods now. And the question is, how do we evaluate what makes a good split? For a classification tree, right? So before we had RSS. Now, some of this discussion about complexity, the cost complexity, you can just replace RSS with something. Or when we were making our splits, we optimize. You go back to our original algorithm, we were optimizing over, way back here, we're optimizing over this whole RSS thing. So the question is, what do we replace that? How do we decide where we split, for example? Which variables, right? We evaluated over all possible variables and all possible splits. We evaluated the RSS in our training data, and we made the split based on that. So for regression tree, the answer was RSS, right? And for a classification tree, we'll need something different. What makes a good split? Node. Well, so for a regression tree, what we do? We would reduce RSS. We want as small RSS as possible. For classification tree, we have what we call node purity or impurity. And what we're going to want to do is we're going to basically play the same game, but we're going to try and reduce, instead of RSS, we're going to reduce the node impurity. Because we're going to want to have a very pure node. So, so either increase node purity or decrease node impurity. So here is an example. Let's just say, example, maybe this is one rectangle, this is another rectangle. If I have in my one rectangle a bunch of red circles and one green triangle, and my other one I have like something like this. Maybe I should use the same color, shouldn't I? Okay, something like that and that. So on the left here we have a very pure node. It has almost all of one type. It's very pure. And on the left, or on the right, we have an impure, where it's basically 50-50 split. So let's say almost all red circles, basically a 50-50 split. So what we want to do is obviously we want to build our classifier. We want to build this tree so that we get very pure nodes, so that presumably that those regions are the regions where it's very likely we're going to have our majority class prediction is going to do better. And there are a bunch of different impurity measures we can look at. So we actually have to have a way of measuring this, right? When we actually go and we split, we're gonna kind of greedily reduce node impurity. We need no way of calculating node impurity for potentially splitting on a particular variable at a particular point. And there are a bunch of different ways you can do this. I'll mention a couple of them. Misclassification, right? Which is 1 minus pk hat, where majority class is class, let's say double k. So that's just percentage of things that are predicted wrong if we were to make that split in our training data. So very pure, this should be approximately 0. Not very pure, this will be approximately 1 over k, something like that. Here, k, capital K, is the number of our classes. But there are other different metrics people have come up with. There's one called the Gini index, which is the sum over my classes of pk hat times 1 minus pk hat. So pk hat here is, sorry, I should explain that, is the percentage in node of class K, in my training data of class K in my node. So here is called the Gini index, and again, pure, if we have a very pure node, the Gini index is about 0. And if we have an impure node, it's again about 1 over k. And you can think about why that would be for that case. Another thing we can look at is called entropy. You could try to calculate entropy, which is a measure of how kind of uniform things are. So this would be, I'll just write the formula, it's negative the sum pk hat times log of pk hat. I sum over my classes. And again, if I have a very pure node, this is about 0, and if I have very impure, this is about 1 over k. So if you notice in my two class problem, Notice they all have similar kind of characteristics, right? If I had a 2-class problem, you could look at on a scale of 0 to 1, like P1 hat. So here, I have 2 classes. I could look on my x-axis. 0% of my node is class 1, or 100% of my node is class 1. And you can actually plot out what these different metrics look like. My misclassification rate looks like a triangle, where its peak is at a half. So this is a misclass. My Gini index looks something like this. And my entropy looks something like this, where all of these kind of hit a value of 1 over k. So you can see they're all kind of doing the same kind of thing, but there's slight variations on each other. But the idea behind a classification tree is pretty much exactly the same as with a regression tree. I'm going to use one of these methods to measure the impurity of a particular node, and I'm basically going to build their tree. So back to my example, I'm going to choose these splits. So I'm going to choose splits at each point, kind of recursively, to split on a variable and split that variable at the point, so that I get, at the end of the day, very pure rectangles. The other way to think of it is it kind of reduces the, you can say you minimize the misclassification. So for example, if you measure purity by misclassification rate, then it would be minimizing the misclassification rate over my training data. I can make these splits to minimize the misclassification rate over my training data. If you use something like Gini index or entropy, you're minimizing the Gini index or the entropy, not misclassification directly, for example. But the idea is you want, at the end of the day, you want your splits to give you kind of very pure rectangles, with the idea that you will do well predicting, because those are very, very sure that those rectangles are one class or another. But the whole discussion about how, basically the algorithm is basically the same, but instead of RSS, you replace it with a misclass or Gini index or entropy. And the whole cost complexity tuning is the same. You're worried if you have too big a tree, you're going to overfit. If you have too small a tree, you're going to underfit. So what typically people do is they build a really big tree and then they prune it back with some cost complexity pruning, and that's how they build the tree. And again, but it's pretty much the same deal as a regression tree. And they're really nice models because they're interpretable, which we'll see in the lab. You can actually just read the decision tree. Okay, but that's a real kind of tour of decision trees, regression trees, and classification trees. We'll look at this a bit in lab today, how to run them, and then we're going to talk about some of the problems we see with these and how we can use these to build some really powerful methods, and how they may seem kind of hokey. They're not. They are can be really powerfully combined in some nice ways. And there's been a lot of exploration over the past 20, 25 years, so relatively recent as far as these methods go, but how you can build really powerful, easy to use algorithms out of trees. So I'll tease that a little bit, and we'll look at that starting next time.